in the last video, we looked at how to compute the likelihood of the parameters. And we saw that the likelihood of the parameters could actually be computed using either the Forwards algorithm for discrete hidden state HMMs or using the Kalman filtering recursions for the linear Gaussian state space model. What I want to do now is take a little bit of a detour to talk about a conundrum which somebody spotted when I first presented this in lectures. And the conundrum goes as follows. Let's back off a minute and consider computing the likelihood of the parameters again. So remember, the likelihood of the parameters is the probability of the observed data given the parameters, and I've just suppressed the parameters in this equation here for a minute. One way we can compute that is just using the sum rule. We can write down the joint probability of the observed variables y1 to t and the latent variables x1 to t, and then sum over all possible settings, all possible sequences, if you like, that the latent variables can take. And I'm going to draw a little diagram to show what this looks like, what all possible sequences look like. This is going to be called a trellis diagram, and I'm going to write it down in the special case where we imagine each of our latent variables can take one of 4 different states, and we've got 6 time steps. So these are the 6 time steps shown here up to time step big T equals 6 at the end, and we can enumerate all possible states that the latent variables take by writing down their value that they could take at each time point. So if you look at the green line here, the green line is a sequence which starts in state 4, then goes to 3, 2, 3, 3, and then 1. And that's one possible sequence. The blue line shows another possible sequence. So here we have to sum over all possible sequences in this calculation. So how many sequences are there? How many would we have to enumerate if we were going to calculate the sum in this way? Well, the answer is it's k to the t. And this is fairly obvious. The first time step, it can be one of k states. In the second time step, it could have taken k by k times k different states, the 4 at the first time step and the 4 different ones at the second time step, and all possible combinations of those, and so on and so forth. So this feels problematic. It's exponential in big T. As the time series gets longer, the number of possible sequences is growing in an exponential fashion. But hang on, how can that be the case? Because our Forwards algorithm just involved a single loop over time. The Forwards or filtering algorithms more generally just considered each time step once and went through the data with linear time complexity. So it seems like we've done something magic here. We've computed a sum over an exponentially growing number of states in a time which was linear in the length of the sequence. So what's going on here? How were we able to sort of do this piece of magic? That was the conundrum that was posed in the lecture. Now, the answer is as follows. Essentially, the Markov property comes and saves us. So let's look at this instance here, where these 2 sequences, I and j, converge. They both end up at state 2. Now, because the history of those processes doesn't matter, where they're going to transition to next doesn't depend on what they were doing beforehand, we can essentially merge those 2 sequences together and just consider the amount of probability that ends up landing in state 2, and then consider where that probability goes. And by doing that, we end up being able to compute this sum, which naively involves an exponential number of terms in a way that involves linear computation in the length of the time series. So this is an example of a more general type of approach, which is called dynamic programming. So the general usage where we use structure in our problem in order to efficiently compute sums is called dynamic programming. It's also called belief propagation or message passing as well. So these are important topics that turn up in a number of different parts of computer science and engineering, and we're flagging them up here as this is one of the most canonical and simplest examples of this sort of type of approaches.